Hello, welcome to my lab on Faraday's Law. This is Lab 5 for Physics 2212. It's on Faraday's Law, of course, and here's the table of contents. So the purpose of this lab is we're going to examine the interactions between a tube of aluminum foil and a magnet falling through its center, and we're going to measure the time it takes for this to occur, and we're going to compare it to a computer simulation. And then from this, we're going to learn about Faraday's Law, magnetic flux, and other things related to this situation. So we have concepts first. Biot-Savart law, that's the law for calculating magnetic fields in general. Then we have Faraday's law, which includes induced EMF on the left side, and then we also have the magnetic flux on the right side. The induced EMF is basically the voltage that comes out as a result, which you can also see in Ohm's law, means that the EMF is equal to IR as well, because voltage is equal to IR from Ohm's law. We have magnetic flux, which of course is a major concept in this, as it is in Faraday's law. And we also, because it is a tube, we also have to worry about the magnetic fields of solenoids, which is another concept that we'll be seeing mainly in the actual simulation. And then we have the Newton's second law and third law, which will be useful in the simulation, the physics 1 concepts that are useful in this lab as well. So and the system itself is the tube of aluminum foil and then the magnet that's going through it. And the surroundings are the table and student center where we were performing this experiment, then any residual electric and magnetic fields from nearby objects, such as my computer, and also just other forces that act in it, like air resistance. So some initial conditions, we had the magnetic bar's velocity set to 0, and then the magnet properties and the aluminum tube properties, we all inputted into the glow script. You can see those properties down here. Those are all initial. So the results, preview of the results. The experiment time was around 1.012 seconds for it to enter and leave the tube, but the simulation time was around 0.317 seconds. It's a lot shorter. That's probably due to some human error on our part. Um, and from this whole lab, from all our results and everything, we did gain a greater understanding of Faraday's law and magnetic flux and other concepts that relate to them. So the experiment itself, we dropped a bar magnet through a tube of aluminum foil, of course. We did this 5 times and averaged the times. You can see those attempts and averages here. And here's the experiment itself. As you can see, that's the experiment there. So now onto the computer simulation. So here's the computer simulation itself. As you can see, we have our tube initial values. We have down here our initial values of the magnet. We have calculation of the dipole moment. That's using magnetic field calculation stuff. We have the actual flux calculation here, which uses a formula from lecture 43 to calculate the magnetic flux. Um, and then we have the actual current calculation here, and then just more magnetic field calculation stuff that leads to magnetic force calculation. And then down here we have implementation of Newton's second and third laws. So let's see the program run. You can see it's falling through the tube, and it does it, and it does the time. Now let's get to some similarities between the experiment and the simulation. Some similarities we saw were that the magnet in the experiment and the simulation, they both generally took under a second to fall, and in both situations, the two major forces that are acting on the magnet were magnetic force and force of gravity. And then, of course, in both situations, the laws of physics apply. Faraday's law is useful for both situations. Magnetic flux is useful for everything. So then the main differences that we saw were that the experimental situation was prone to much more error and could also have dissipative forces marginally affecting the results. However, perhaps the actual simulation also had some error considering how much shorter it was. And then we also saw that the magnet fell faster in the simulation than the experiment, of course. Um, so some possible sources of error, just outside interference from residual electric magnetic fields and nearby equipment, or just human error in tracking the magnet's position or tracking time spent contained within the tube. There's probably some air resistance to some degree that could have led to some error. And then just error in measuring the aluminum foil present on the tube, and then the properties of the magnet. So some discussion. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Well, Ohm's law means that reducing the resistivity would increase the current, resulting in a greatly increased upwards force, which results in the magnet either having slow descent or just not descending at all or being pushed up from the tube. So what if holes or slots were cut into the tube, and how would this affect the ring currents in your model? Well, current is disrupted, reduced due to the holes and slots have been cut into the tube, decreasing the total current of the solenoid, resulting in decreasing magnetic force. This would, of course, mean that the magnet has less force pushing it up. The force of gravity stays the same, so the magnet falls faster with the holes. So some conclusions. Again, we have the times that we stated before. And then from this lab, we explored the concepts surrounding Faraday's law, and we experimented with a real-world example of Faraday's law and other concepts related to electricity and magnetism. And another big part of this was we gained a better understanding of flux, specifically magnetic flux, and just how it relates to Faraday's law. Thank you for listening to my lab.